Hey everyone, welcome back to TryHackMe's Advent of Cyber 2. I'm Dark, and today we're going to do Day 7, The Grinch Really Did Steal Christmas. And it looks like today is going to be a Wireshark-focused day. Now, I've had a look ahead at the next couple of days, and I think you guys will have a lot of fun. We've got a lot of fun activities coming up. But without further ado, let's go ahead and jump into Day 7. Now, for today, I'm not actually going to be using the TryHackMe attack box. You can do this if you want. For using the TryHackMe attack box, we're going to download these. This is a set of Pcaps, so just collection of packets as they would travel over the wire. You can download this on the attack box and do this activity 100% through it. I just find Wireshark to be a little bit easier to use on my native Kali, and it'll be easier for you guys as the viewer to actually view what I'm doing. If you want to do this on the attack box, go ahead and spin up the attack box. Click download on here after logging in, and you should be able to do it just fine. Alright, let's jump right in. So, story. It's 6 a.m. and Elf McSkitty is clocking in to the Best Festival Company's SOC headquarters to begin his watch over TBFC's infrastructure. After logging in, Elf McSkitty proceeds to read through emails left by Elf McSkitty during the night shift. More automatic scanning alerts. Oh look, another APT group. It feels like it's going to be a long but easy start to the week for Elf McEager. Whilst clearing the backup of emails, Elf McEager reads the following. Urgent data exfiltration detected on TBFC-Web 0-01. Uh-oh, goes Elf McEager. TBFC-Web-01? That's Santa's web server. Who's the motive to steal data from there? It's time for the ever-vigilant Elf McEager to prove his salt and find out what exactly happened. Unknowingly to Elf McEager, Elf McSkitty made this all up. Fortunately, this isn't a real attack, but a training exercise created ahead of Elf McEager's performance review. I haven't seen this happen in the wild. I'm sure it does. If you work in an environment where you've had this happen to you, where you've seen something come across the SOC and it ends up being involved in your performance review, please comment about that. I would love to hear about it. So, learning objectives. Today we're going to talk about what are IP addresses, how they are assigned, understanding the TCP model and UDP, so different ways that we can transmit packets, looking at the three-way handshake. We're going to do a quick crash course on Wireshark, where it's used and why, and basic filtering and operators with that, as well as we're going to analyze our first few Pcaps, looking at HTTP and then SMB traffic. And then we're going to end today off with a challenge. And CM Natick, who's actually a part of the TryHackMe team as well as a moderator on the Discord, made today's challenge. What is an IP address? You'll hear talk of the term IP address frequently throughout the information technology field, not just TryHackMe. Short for an Internet Protocol address, I'd like to explain the fundamental of networking using the same way that the postal mail system works in real life. When sending a letter, you need to provide an address for where the letter should go, and it is best practice to include your address as the return address in case the letter is lost, or you wish to let the recipient know how to reply. An IP address serves the same purpose, but for devices connected to a network. Devices connected to the internet will have two of these addresses, a public and a private IP address. Think of a private address as the name of the recipient at a business, so for example, Joe Smith, and the public address being the location of the business, so for example, 16 Kemp Road, London. So you have two parts of your address. You have who it's actually going to, and then you have the broader location that it's going to. Let's say you're accessing the internet through your computer, like we're doing right here. Your computer will be part of two networks, and in turn will use both public and private IP addresses. A private IP address is to identify itself amongst other devices such as smartphones, TVs, and other computers within the network of your house. So just the private network. This can be your school network, this could be your dorm network, this could be your apartment's Wi-Fi, or maybe the Wi-Fi at a Starbucks hotspot, something like that. In the screenshot below, the two devices have the following private IP addresses. So it looks like we have a CM Natick PC and then just a normal, this looks like a Windows computer given the random IP that's generated there. And here we can see that we have an IP address for each one of these, and this has to be unique. And then we have the MAC address as well, which these have to be unique. In theory, globally, but it's very rare that these line up unless you're on a really, really big network. These are assigned, they're what's referred to as burned in by the device manufacturer. The IP address is set by your router. You don't need to know too much more than that for today. Just think of this as your IP address is typically the main thing that's used when you are connected to a network, and that way your traffic can get back to you. Similarly, TryHackMe uses these private addresses. For you to access other TryHackMe devices, such as the instances that you'll deploy in this room, you will need to be on the same private network as these instances aren't connected to the internet. So you need to connect to the actual network that we have. This is why you must use a client such as the OpenVPN to connect to the network. Muirland Oracle explains how these private IP addresses in his work in his room intro to network, and I definitely recommend checking this out. I'll have it linked in the video description as well in case you want to dig a little bit further into that. I think this room is free. I will put a little note in parentheses after it if it's free or a subscriber in the video description. A private IP or a public private or a public IP address was given by your internet service provider, often shortened to ISP, that identifies your house on the internet. The internet is just many, many networks connected. Using our example from above, the two devices will share a public IP address to identify themselves on a network. So here we can see we have a public IP address, and this one's just going to typically say your ISP who owns that public IP, and then your rough location. And here you can see that these two devices, even though they're on the same private network, share the same public IP. Sometimes you can have multiple, in the case where you have a lot of devices on one network, you'll have multiple public IP addresses, but that's more so of like big company, or if you're working, if you're on a school network or university network, that'll be what happens typically. This is achieved through NATing. This is a network address translation. So your router, essentially, think of the old address book that your grandma probably has, where she would keep track of, you have a name and then you have an address, and you can search through it alphabetically. Your router does the same thing for your devices. So it says, hey, it's coming back. We already had an active connection from device A. So for example, Seamnatic PC. And it's connected to device B, which is out on the public internet. Your router keeps track of that, and it's in part of the routing table. I can't remember the technical name of that. Part of that is done with your MAC address there. I won't go too far into it, but think of it this way. Your router keeps track of all that for you. So, very, very simple, and I recommend taking a look at this. This is a nice explanation of how NATing works. And this details how this works, but it's, again, a bit beyond the scope of today. Protocols 101. With the internet predicted to have 50 billion devices, and you read that correctly, by the end of 2020, so right about now, Cisco, which has an article on that, chaos quickly ensues if there are no ground rules in how devices should communicate with each other. If this is a bit confusing, I don't blame you, just bear with me here. Think of it this way. You use protocols in everyday life. When talking to someone, you will use the same set of protocols, otherwise no one will understand each other. At the very least, all parties wishing to converse will use the same language, and that's our protocol. Other protocols may include the context or topic of the conversation. If anyone strays from these protocols, they risk not being understood. This is the same for network-connected devices. Back to the technical stuff. Enter protocols such as TCP/IP and the UDP/IP models. With TCP/IP being the most commonplace today, we'll discuss this further. We're going to dive into that in just a moment. TCP/IP is a protocol that ensures that any data is processed in the same order. So first in, if you have a packet number 1 and then packet number 2, packet number 1 will always be processed before packet number 2 with TCP. Going back to our postal system, your letter will go to many places, even when sending domestically. It's just a what place is busiest or what place is least busy, and it just gets sent to that typically. Your computer traffic does the same, going from device to device in a process called routing. One device should deliver data quicker and as a result in a different order, than causing a headache for the situation where accuracy is important, such as the following. So downloading files because you want everything in the file to be in the right order. If it's not, that file is going to be corrupt. Visiting a website in your browser. Imagine if this paragraph was after this paragraph. It would be very confusing. Sending emails. This is unlike the UDP protocol where all packets they're not quite important for the ordering, making the protocol a lot quicker than TCP IP, which is why the majority of applications like video streaming make use of UDP. And I was hoping that Skype was going to get mentioned here. That is a classical one. Skype gets brought up for UDP pretty regularly, just because you're sending out all the packets. You don't necessarily care if they... Sometimes you'll see the video stutter if you're using Zoom or Skype, or it'll like revert back to a previous frame for just a second. Sometimes that happens, but when you're using something like video streaming, you don't really care. You care that, the most of them make it there. We don't really care if a few packets are lost, as we can still see a majority of the picture. How does TCP IP send data? Enter the three-way handshake. The three-way handshake is a method that makes TCP reliable. Any data that is sent is given a random number sequence and is reconstructed using this number sequence in incrementing by 1. So that's, in English, this means, think of it this way. Packet 1, packet 2, packet 3. They are in that order. And when the computer that receives them, if it receives packet 3 and it hasn't gotten packet 2 or even packet 1, it's going to say, hold on, I can't do anything with this, and it's just going to wait. Sometimes it will throw out the packet, sometimes it'll just let it sit. It depends on how it's configured, but long and short, TCP IP, it is going to receive it in the order that it was sent. Both computers must agree on the same number sequence for a data to be sent in the correct order. This order is agreed upon during 3 steps. In the diagram below, the client has the initial sequence number ISN of 0, where the server has 5,000. Any data sent from the client and received on the server will be initial sequence plus 1. So this is just incrementing. It's just saying that when you send a packet, it's just going to keep going up, and it's incrementing the packets to keep track and make sure that packets aren't necessarily missed. If this is the first packet from client, this would be 0 plus 1. I've shown 3 packets being sent from the client in the table below to help demonstrate this. So you see we have packet number 1 being sent here, that becomes 1. Packet number 2 being sent here, even though it has the initial sequence number, that becomes the final sequence number of 2. So it's incremented after it is sent in this specific case. And you can see it going back and forth here. So we're just making sure that we are expecting these packets to be in order. And this ends up having the format of SYN, SYNAC, ACK. These are flags that can be set within the packet. This is a synchronize flag. So it's saying, hey, I'm sending this initial packet, a SYN packet, to with my ISN, so my starting sequence number, to your server because I want to start talking to you. It's essentially, hey, how are you doing? Or something like that. Then we send the server in this specific situation is going to send back a SYN ACK packet. It's going to have 2 flags set, one SYN flag and one ACK flag. And for those of you that are doing a CCNA or something like that, you'll spend a lot of time going through this specific section. It's something that they cover pretty heavily, and knowing the full OSI model is also great to know with this. So here we can see that we're sending back a packet from the server to the client with the SYN flag saying, hey, I have initial sequence number of 5,000, and I acknowledge your initial sequence number, your ISN, of 0. And then we have an ACK coming back from the client that says, okay, I've seen that you've acknowledged that, and you sent me back your SYN number. I'm going to acknowledge that your ISN is 5,000. Here is some of my data with an ISN of +1. So it's going back and forth, just confirming that we're all starting from the same number, and it makes sure that that order is established from the get-go of the communication. When the data is received, it is reassembled by the receiver. Let's show the conditions of which reassembly is required. So examples of TCP reassembling data. No reassembly required. If the server were to receive data that was received in the exact order it was sent from the client, so if we send our first one and then it's received, and then second, and then third, we don't have to reassemble that because everything came in order, wasn't screwed up. we have to do some reassembly if things start coming out of order. So for example, in this next diagram, we can see that we have the first one sent and then it's received. And then we send our second one and we're wondering what's going on. And the computer sends the third one and the third one gets there before the second one does. Sometimes that happens. Amazon does this too. It happens. You've probably gotten mail in the wrong order or not the order you have expected it in. And the computer is going to say, hey, hold on, I need to reassemble this because these ISNs don't match up for these two packets. And it might go back in order after that. Sometimes it gets even more out of order, and the computers, they just take care of it. That's the magic of having the networking all done automatically, either by a networking card that was added to your computer, or you just have your port and they specified chips on the motherboard that take care of it all for you. There's a lot more to it than that. I'm oversimplifying it, but generally speaking, this is all done automagically. Connection is dropped. So if a client was to send 3 packets, but the server only receives 2 out of the 3 packets, they are disconnected from each other as the data is corrupt. So say we send our first one, and then it's the first one received, and then the second one sent, and it just never gets there. And then we send the third one, and this one ends up being received second. We know that this one's just gone, and we say, hold on, there's a problem here. This connection has some issues. Let's try again. The data will not be processed by the server, as the packet that was sent second by the client was never received by server number 2, meaning there was some loss of data along the way, which is something that the TCP model will say, hold on, I can't do this. All right, let's take a crash course in how we can actually observe this with monitoring our network traffic. Because right now, this is probably a lot of ephemeral things. We're going to take a look at how we can actually see it. Being able to capture exactly what is traveling across a network and understanding this is an important skill. It's worth understanding that this is an important skill within information technology. From diagnosing to capturing credentials, positions in IT ranging from system administrators to digital forensics to us pen testers all use network traffic in their own ways. For example, since data sent via HTTP or FTP is unencrypted, a pen tester might be able to capture usernames and passwords being entered into a website. It's not uncommon just to sniff network traffic if you're sitting, for example, let's say that I am on a company's network and I'm doing a pen test for them and I just want to sit and listen to the traffic. Sometimes there are specific tools that will do this for you that will sniff for passwords. You can just take a sample of the traffic and see what you're working with. This is good for a number of reasons. A lot of times you'll do this to see what protocols they are using and see if there are different things that can be abused. Responder is typically the tool that comes to mind. That's something that I recommend doing some more research into. I believe Throwback has some use of Responder, so that's something that I definitely recommend looking into. I think Attactive Directory, which I will link down below, will have that too. Introducing Wireshark. Wireshark is capable of recording a log of all the packets sent and received on a computer's network adapter. For example, we can see how a computer highlighted in red down here connected to a computer highlighted in black. So we have our source and destination that was running a web server via HTTP, and we can see our protocol right there. In this case, it was the web server. We're seeing this connection actually happen in real time. So here we can see that it looks like we have the base, just the download.html file that we can see this pulled out of the network packet capture just down here. And we have this full page. It doesn't have any of the styling because that's a different file from the HTML file. Most of the time you can do that in the HTML file, but that's conversation for another day. But you can see we can just pull that out of the network traffic. As it's not encrypted, it's HTTP. Networks are, however, rather noisy. Wireshark captured 2,648 packets after a single minute on his machine, on CMNATIC's machine in this specific case. With bigger networks, this can be a lot more. There's a lot of traffic that goes. The computers do a lot in the background. Even when you think they're idle, they're doing things. And you can see that if you have activity lights on your computer, take a look at them every once in a while and just see what's going on. This makes analyzing very hard. Thankfully, we can use filters to narrow down the results. We can filter by many things, but we'll only cover a couple of important ones in the table below. Note that all the examples use the double equals operator to see if the filter exactly matches the value we give it. So let's see, we have 4 filters that we're going to take a look at. We have the IP source, IP dest, the TCP or UDP port, and then the protocol request method. So in this case, the first one, the IP source, is going to be looking if we can match on the source of the traffic, the source IP address. Similarly, we have the destination IP, and we have the port that is going to be used. So we're going to look, one, is it UDP or TCP? And then what port is it going to? And here we can see we have one of our common TCP ports up at the top. That is going to be for SSH. So if we wanted to see, all SSH traffic that happened in a network capture, we could look for that. And then this, last but not least, the protocol.request.method is going to allow us, for example, we can select HTTP, and we can look specifically for get or post requests and submit data accordingly. This is going to allow us to just filter down by what protocol, and then specifically these requests that we want to see the data from. In the case of web requests, especially with HTTP, since it's unencrypted, this is very useful as we can get a lot of data very quickly. And even then, sub passwords and usernames that can be very, very useful to us as pen testers. In the screenshot below, I used the filter IP.source to list all the packets that were explicitly sent from the specific address using the equals operator to define what host I wish to search for. We'll quickly explore the use of these operators in the next section. So here we can see all of our source IP addresses are matching, and then the destination can be a little bit different, but we can use that to whittle things down. Combining filters with operators. So we have 3 operators we're going to take a look at. This is where you start getting into Boolean logic. Boolean logic, if you've studied any programming, will be very second nature to you. I'm going to break down some of the basic ones that we're looking at here today for those who might not have experience with it. So the first operator, double equals. This is an operator to use to check and see if the filter, so for example, IP.ADR, so the IP address, matches the value given in all the packets. So we're looking for an exact match. This is, I want something that is equal to this. This next one is going to be, I want something that's not equal to this. So maybe we don't want to see traffic from, or traffic that includes this IP address at all. Maybe if we're doing digital forensics and we are doing a packet capture with, I can't remember what they renamed it, but it used to be Molach, spelled M-O-L-A-C-H. You can do packet analysis with that, and maybe we have a host that, okay, I don't care about my domain controller because I know that this one wasn't infected and it wasn't doing anything with the attack. Or it was off at the time of the attack and it's not doing anything. Maybe we have packets from the time of an attack and we want to try to get the outbound communication from an infected host to the command and control server that is actually responsible for whatever your attack you're dealing with. You can use this to filter out crap you just don't want. And then we have double equals. This is something that this is the AND operator that we can use to combine multiple filters together. So it means both of these things need to be true in order to have results actually show up in our search results here, or packets rather show up in our search results. So we can see that we have, it looks like we want something that we want all the communication between 192.168.1.1 and then .10. And we want, we don't really care which one's the source or destination. We just want all packets that have these IP addresses in there. Great way to get an entire conversation that happened between computers in that specific way. Exporting data from Wireshark. As previously shown, Wireshark is capable of exporting data from protocols such as HTTP by navigating to File and then Export Objects. We'll go into this in just a little bit. I believe we need it for one of the questions. And selecting the protocol available. So we're going to select File, and then we'll go to Export Objects, and then we select what protocol we want to export objects from. Typically, SMB can be very, very useful. TFTP can be useful to get downloads and things like that, and then HTTP as well. We'll export the text.txt file onto our device. So here we can see that we have all of the objects that are found, all of the files of various different things. There's some interesting things on there. We won't worry about that. But you can see that we can view like different text files, and often enough you'll find pictures or other weird things in here, or HTML files. And we can just export it here. There is an export all button as well that makes it a little bit easier if you want to go through them very quickly. And then we have our challenge. So what I'm going to do is I'm going to go ahead and pause here for just a moment. If you want to do the challenge on your own or attempt it now, I recommend pausing the video and then coming back once you are done, or if you get stuck. Otherwise, after the break, we're going to go ahead and go through the challenge ourselves here on the channel. We'll be right back. And welcome back. We're going to go ahead and dive right in here. Now, if you're doing this on your own Kali machine like I am, Wireshark might not actually be installed. I learned that it's not installed by default now, so that's a thing. If you need to install it, you can do that with, here, we'll clean this up. That command, apt install Wireshark, you might need a sudo at the beginning, like that. But if you need it, just install it like that. Very, very easy. It's in the apt repository for Kali. Very simple, and you should be off to the races. So, once you've got that, you can go ahead and open up Wireshark and then just drag one of the Pcaps in, and it should be nice and easy. One quick note, I did have to extract these. If you are having any issues with them, make sure that they're not in a zip file still, just for a sanity check. All right, let's go ahead and move into our questions. So download the zip file, aocpcaps.zip, that is attached to this task. Use a combination of the filters and features of Wireshark we've covered to answer the questions below. So let me show you where you can download that as well. That is at the very top, and it's easy to miss if you're not careful. So if you go up to the top and you click on this, you can go ahead and download it. I've gone ahead and already done that, so I won't do it in this case. But in case you missed it, you're like, you want me to download something? I don't even know where I'm going to download it from. You can get it from that. So nice and easy. Let's go ahead and use a combination of the filters and features of Wireshark we've covered to answer the questions below. Our first question is, open pcap1.pcap in Wireshark. What is the IP address that initiates an ICMP/ping? That is actually going to be our first one here, and this might be a little bit tricky to see, but you can see this is a, let's see. There we go. It's this first one. You can see that Wireshark has correctly identified this as a ping request, and you can see this is our first one here, so it is very likely the ping request that we're looking for. We can see our source IP address here, though, and that is going to be 10.11.3.2. If we only wanted to see HTTP GET requests in our pcap1.pcap file, what filter will we use? We can do that with the http.request.method == get. And we're actually going to do that in a moment. So we'll do HTTP request, and then we'll go down to method == get, and we can search for that, and there we go. So we have that. Now apply this filter to pcap1.pcap in Wireshark. What is the name of the article that the IP address in question 1 visited? So we're looking for 10.11.3.2, and we can actually make this even easier and do ip.source == 10.11.3.2, and we'll do IP-adder instead. Maybe. Or maybe not. Let's see. Let's see what we get. Looks like we only have one. So I will go ahead and we'll be right back. I'm going to troubleshoot this for just a moment and we'll figure out what we're looking for. So it looks like there's a small typo in that question. That will be fixed by the time that you guys see this. However, we're specifically looking for this post that we're looking for. Or this post, rather, from this IP address. So we have 10.10.67.199, and it was looking for a Reindeer of the Week article. And there we go. So we'll get that updated as well. All right, let's go ahead and jump into PCAP 2, and we'll do our next question. We can go ahead and jump in by just dragging that over, and we're going to get rid of our filter, as we don't really need that anymore. Let's begin analyzing PCAP 2. Let's look at the captured FTP traffic. what password was leaked during the login process. So let's go ahead. We can search specifically for the FTP traffic by using the actual port that is involved. And we have one of our filters for that, which we can do with tcp.port. We can do == 21. And then we have all of our FTP traffic for the most part. Could there be other stuff running on 21? Yeah, but generally speaking, this is going to be FTP traffic. So now what we can go ahead and do is we can, let's see if I can follow TCP stream. There we go. Follow TCP stream. I just right-clicked for that. And then we'll go to, looks like that was the entire conversation there. We're going to get rid of, we'll go back with this filter. And it looks like there's a couple things that happened here for TCP with FTP being involved. Since that was just a failed login attempt, we can do that, however, with our next request here. And it looks like this one was an actual successful login, so we can go to follow, and let's try this now. There we go. So we have our password there, and if you can't read it, that is going to be plain text password fiasco. And there we go. And that'll do it for that one. Continuing with our analysis of Pcap 2, what is the name of the protocol that is encrypted? That is going to be SSH in this specific case. And we actually saw it a little bit here, and we can see it up at the top. There we go. Let's go ahead and jump into Pcap 3, and we can recover Christmas. So Pcap 3. Interesting. So it looks like we have a lot of, we have some SSH traffic, and then we have some HTTP traffic. And I think our HTTP traffic, if I'm guessing, is likely going to be the most interesting one. Let's follow. That is a big stream of TCP. Let's draw that and see what we've got. And that's a lot. It looks like a download to me. So we're going to go ahead, and there we go. TryHackMe full logo. Let's see what objects we have in here. And it looks like we have, we have the getChristmas.zip. So if we go through and grab that, we should be able to get a zip file out of this, and we can just extract the items from that. So we'll go ahead and go to HTTP, and it looks like we have Christmas.zip. We're going to go ahead and save that, and we'll go up. Here, one second. Let's go ahead and go, we'll save it in the root directory, so that'll be fine. Give me just a moment. I will go ahead and get that open. We'll be right back. And we're back. I had to change the ownership on that because I have Wireshark running as root because of the permissions that it requires. But I've gone ahead and extracted that, and we should be able to take a look at everything that's here. And it looks like we have, that's a nice background. I think this is the background of our attack box, so if you want it, here you go. Have some fun. We have a picture of a Christmas tree. That is a nice looking tree. Looks like we have a wish list. And then this seems to be the answer to our question, along with Operation Arctic Storm. Oh my god. Someone had too much fun with this. Okay. That's great and also terrifying. And it looks like we have the TryHackMe logo. If you need that for things, have fun. And what I can only assume to be dubious material right there. What is on Elf McSkitty's wish list that will be used to replace Elf McEager? It looks like we have a rubber ducky. Sounded about right. Okay, and there we go. That is going to do it for day 7. I will see you guys tomorrow on day 8. However, if you have any questions, as always, I have the TryHackMe Discord linked in the video description as well. And otherwise, I will see you guys tomorrow with day 8.